Hi, the purpose of this video is to overview the presentation that's going to be done at a parent math night at the Gilbert Public Schools at Greenfield and at Agritopia campuses. So this is a brief overview. It won't be the full hour, just a quick breeze through the ideas. The overall idea is that we're trying to help our students to make sense of mathematics and not just perform algorithms without making sense of them. And so here's how it's going to go. First of all, we're going to lead off with a little context. Back on August 14th, 1944, Dietrich Bonhoeffer made a quote, and the quote was this: "God does not give us everything we want, but he does fulfill all his promises, leading us along the best and straightest paths to himself." Now this is just to kind of give a biblical integration here a little bit, but the big idea is, the big mathematical idea is this: how many years was it from 1944, August 14, 1944, to August 14, 2023? And how would you figure it out? So I'm going to ask the parents this. I'm going to ask you this now. Just pause this video and take a moment, just inside of your head. How would you think about finding the number of years that have passed from August 14, 1944 to August 14, 2023? Pause the video and think for a moment. Now, my expectation is that sitting in a room, as I'll be making this presentation, I'll ask parents to think about this. We'll have them share. I'll ask for some volunteers to share. But here's the idea. It is most likely, because I've done this kind of a thing before, it is most likely that very few, if any, of the parents of an adult would do this. First, step one, notice that this is a subtraction contest. Step two, set up the problem using the template, the vertical subtraction template. Step three, work right to left. Look at the 3 and the 4. Realize you can subtract 4 from 3. Remember that you should borrow from the next column to the left. And you might wonder, why are we borrowing if we're never going to give it back? But nonetheless, we borrow from the 2. We make it a 1. And we bring the next 1 over to the 3. And we wedge that little tiny 3 between the 1 and the 2. And we might put it a little higher than the 3 just to kind of help us to see it. And so we'll have that 13 minus 4, and we'll get 9. We write that answer at the bottom right-hand corner. Step 8, we realize on the next column that we can't subtract 4 from 1. So now we have to borrow once again to the next column from the left. But the problem is there's nothing there. It's a 0. There's nothing to borrow. So we have to go all the way to the far left and borrow from that 2, make it a 1. Again, think of the 0 as a 10, wedge a little tiny 1 between the 1 and the 2 and the 0. We might want to make it a little higher than the 0, but now we have a 10 there, so now we can cross off the 10, make it a 9, borrow from there, and bring the 1 over to the other one, and maybe again wedge it up there a little higher, but nonetheless we have 11 minus 4, which is 7. Then, on that third column from the right, we have 9 minus 9, which is 0, and then we go all the way to the left column, we have 1 minus 1, which is 0, and then we declare the answer to be 79. 17 steps. So in this case, the traditional algorithm is not so efficient. And in fact, when asked, I've done this a lot of times, I've seen lots of strategies, I've collected some of them, and maybe in the night of this parent night, we'll see some of these strategies emerge. Here's one strategy. Sometimes people start at 44, and they can get to 2000. They can see 56. Like 50 would get you to 1994. 6 more gets you to 2000. They can see the 56 years getting you to 2000, and then the 23 would be another 23 years, give a total of 79. So they're kind of like counting up from 1944 to 2023. Other people might start at 1944 and just add a full 60. That gets us to 2004. And then now from 2004 to 2023, they might be able to see there's 19 more years. So 60 plus 19 is 79 years. Sometimes people count by tens, 44, 54, 64, 74, 84, 94. They keep counting by tens until maybe they get to 2024, and then they go, oh, I just made it one too many. So they'd have done 8 sets of 10. They would have counted by 10 8 times. That's 80 to get to 2024, and then back up 1 year, 79 years. Or sometimes people shift the whole thing by 4 years. Instead of 44, they'll just shift it to 1940. And instead of 2023, shift it by 4 years to 2019. And now the counting on is a little bit easier. From 40 to 2000 is 60, and then 19 more, 79. There's all kinds of strategies that people apply. And so we're going to make this point that that's exactly what we want. We want students to think and reason about the situation in the context they're given and then apply the proper way of thinking. And that's what we're trying to encourage. We're encouraging the development of ways of thinking that are empowered by habits of thinking. And then once those habits of thinking are indeed habits, then students have the ability to make sense and use some ways of doing that lead to even bigger things with mathematics. And so notice the ways of doing, and you saw 4 different strategies there, are at the end of the thinking. Now, what I've seen in my career is a lot of times students start with the doing. They go, oh, what am I supposed to do? What am I supposed to do? They try to remember what to do apart from the thinking. So what we're encouraging is developing ways of thinking, different strategies, and then the ways of thinking inform the ways of doing. And that's what fluency is. Fluency includes thinking about mathematical procedures efficiently, accurately, flexibly, and appropriately. Being fluent means that students can choose flexibly among methods. You just saw 4 different strategies that people might have employed in my Bonhoeffer situation, and they were flexible to choose the one that made the most sense to them in that particular moment. To solve contextual and mathematical problems, and they understand and are able to explain their approaches, and they're able to produce accurate answers efficiently. So fluency certainly is about accuracy and precision, yes, but it's also about flexibility, it's about understanding, it's about appropriateness, and it's about ultimately being efficient. But what's efficient? Efficiency is in the eye of the beholder. It wouldn't be efficient, in my opinion, to employ the standard algorithm in this case. 17 steps later, we get to the 79. It might be more efficient for somebody in a moment, depending on the context, to employ some other strategy, like the counting by 10 strategy, as an example. Now, accuracy includes 2 things. Certainly the computational accuracy. We want students to get the right answer, like the 79 years from 1944 to 2023, but we also want them to be able to communicate accurately. We want them to be able to explain their thinking and describe it and use proper mathematical vocabulary. And we want students to be flexible. Again, just showing this problem, the standard algorithm of borrowing 17 steps later when there's probably other ways. And so flexibility is an important thing. And in fact, watch this. Suppose a student needed to subtract 12 minus 9, and all they know is the standard algorithm. Borrow from the 1, make it a 0, carry the 1 over to the 12, and notice you're right back to 12 minus 9. And so it would not be appropriate to use the standard algorithm in that case. It might be more appropriate to have another strategy, like we call it counting on. 9, 10, 11, 12. 12 minus 9 is 3 because there's that difference of 3. So we want to encourage our students to be aware of appropriate strategies as well. And then, think about this. Suppose you had to add 135 plus 115. Just think for a minute. Now, real life story here. I have a 6-year-old, Adonis, and Adonis was in the garage while my son and I were working out, and we were writing our numbers on the whiteboard to keep track of what we were doing, and we were lifting weights. And so Adonis decided that he should add these numbers together. You can see he was adding these, and then he was about to add these, and I saw what he was doing, and I had to record it. I'm not going to take the time to play the recording here. I'll include the recording as a link, but watch Adonis think. He's 6 years old, just started first grade. Watch how he thinks about adding these numbers. He doesn't do it from he doesn't even know the traditional algorithm yet, because in first grade we typically don't have 3-digit addition, but nonetheless he has ways of thinking, and for Adonis at age 6 has efficient ways of adding these numbers. Watch that video and see if you see what I'm talking about. Now what about this one? Fractions. Fractions are always a challenge for students and adults alike, but how do you think about 1/2 times 6/5? Is your first thought, oh wait, how do you do that? Do you cross multiply? Do you get a common denominator? Oh, what do you do? What do you do? Or are we thinking about, what does this mean? And I want to challenge you to think about what multiplication means. Now, often multiplication is given as a repeated addition idea, which is true, but not complete. 6 times 4, you might think, means to take 6 and add it 4 times. 6 plus 6 plus 6 plus 6 is 24. Then if you get to fractions, let's see if that persists. 6 times a half means take 6 and add it a half a time. Do you see the dilemma? It gets a little more awkward to take 6 and add it a half a time. I can take 6 and add it 4 times. It's hard to take 6 and add it just a half a time. How do you add something only a half a time? Now, if you do the commutative property, you can do a half times 6. You can take a half and add it 6 times. A half and a half is a whole. A half and a half is a whole. A half and a half is a whole. There's 4. A half and a half is a whole. So we can get to 3 that way. That's good. But 6 times a half. And then if you have 2 fractions, what if you did just repeated addition? Add a half 6/5 of a time. Now it gets really awkward. And so what do? Well, I would like to encourage this meaning instead. We use the phrase copies of. 6 times 4 is 6 copies of 4. Can you imagine a 4 and a 4 and a 4 and a 4 and a 4? And if you had 6 copies or 6 groups of 4, you'd have 24. Or can you imagine 6 copies of a half? Half and a half make a whole, half and a half make a whole, half and a half make a whole. You can imagine 6 copies of a half, and you can maybe see 3. But that even works in the last one. Can you imagine a half of a copy? Can you imagine 6 of something, and then half of it? Taking half of a copy would get you to 3 as well. And you can do that here. Imagine half of a copy of 6/5. Imagine you have 6/5, but we just want half of a copy. Well, half of 6/5 would be 3/5. See, you don't need any algorithm. You don't have to go, oh, what was it? Do you cross multiply? Do you get a common denominator? Instead, we focus on what does multiplication mean. And we do this, by the way, with everything. What does addition mean? What does subtraction mean? What does division mean? What does anything mean often drives what you should do. So if I know that multiplication means copies of, I can think, well, what would be a half of a copy of 6/5? Half of 6/5 would be 3/5. Now here's the challenge. I've worked with some schools in the past, and I did a little study, just a little mini personal study here. I interviewed about 10 fifth and sixth graders, and I asked them this question. And over half of the students enacted an incorrect algorithm. They did the thing. They went, oh, wait, I think you're supposed to cross multiply, or I think you're supposed to do something. Over half of them enacted an algorithm that was not correct for this problem. And some students said that they're supposed to cross multiply. One student found common denominators and added, even though multiplication was the goal. And they were aware of that. I challenged them. I said, what is the problem? Wait, I'm multiplying, so I need a common denominator. And you don't. Half of 6/5 is just 3/5. So we have a problem here with students just learn to kind of blindly follow the rules. In fact, one student did this. He said, first of all, because he's thinking about doing, first of all, I have to take 6/5 and make it 1 1/5, which is true. You can see that there in the arrow. And then he said, multiply a half times a fifth and get a tenth. He multiplied straight across. 1 times 1 is 1. 2 times 5 is 10. And he got a tenth. Now you'll see that you're seeing the ending work here, so you're not seeing the 1/10 exactly there. But then he said, now you put the 1 back in. That 1 that we had, the 1 1/5, now you put it back in is the words the student used. But he left the numerator blank. He ended up erasing the 1, or maybe he didn't write the 1 in the first place, but he left a blank there. Then he said, I have to get a common denominator. The common denominator between 5 and 2 is 10, and so the 5 needs a 2 and the 2 needs a 5. And then he said, now I add those 5 and the 2, and I get 7. So he had 1, actually he had 6 first. He changed it to 7 a little bit later. So he had 1 7/10, and he gets 1 7/10. What in the world? This is a mishmash of a bunch of algorithms that the student learned, because that's been the experience, is that math is just about remembering to enact some procedure, some set of rules to get the right answer. But after you learn a bunch of those rules without understanding, they're just like mishmashed in the brain, and we see these kinds of things happen. One student did this. They said, well, with fractions, you have to flip the fraction. There is a time that you would do a reciprocal, but not in this case. So they took the 6/5 and made it 5/6. And then they said times a half. And they said this. If you look at the denominator, they said half of 6 is 12. Half of 6 is 12. And so I asked the student, I said, could you clarify, how is it that half of 6 is 12? Well, yeah, because with fractions, half of 6 is 12 instead of 3. Now again, what they're remembering some rule that they learned and that applied to some case, but they're applying it in the wrong time. And so this is the challenge. When just rote memory is the predominant method of trying to get students to learn their basic facts and to develop fluency, we have these kinds of things. We have inefficiencies. Memorizing by rote is very challenging, and many students just give up. If there's no meaning attached to the memory, it's hard to remember things that don't make sense, and so students give up, and we have some inefficiencies. Or we have what I just described, the inappropriate applications. When you're just memorizing by rote instead of making sense, students misapply the knowledge, as you saw in those case studies. Inflexibility, students are unable to use or create a strategy that is best. The 1944 to 2023, the standard algorithm may not be best. It might be better to have other strategies, and then so we end up with inflexibility when all we have is the standard algorithm, 12 minus 9. 12 minus 9, if you just enact the standard algorithm, results in 12 minus 9. You're right back to where you started. And so what is the science behind fluency? It's developmental. There's stages or phases that students go through to develop this fluency. In phase 1, there's just counting strategies, concrete. They use their fingers, and that's a good thing. When students are using their fingers, the brain is able to see better what's happening. Let that happen in phase 1. Then we move into phase 2, and students develop reasoning strategies, different strategies to help them make sense of the mathematics. And also in that phase is where we really emphasize what addition, subtraction, multiplication, division, for example, in elementary, what do those operations even mean? And then finally, as students have all of those foundational understandings, then we can focus on phase 3, which is that mastery, to become efficient, to have an, they call it automaticity, to have some automatic result. 8 times 6 is 48, because I know it is. But if you ask me, I could also unpack for you like a phase 2 reasoning. I could tell you why 8 times 6 is 48. I could tell you what multiplication means. And I could even go back to phase 1 and show you what 8 times 6 is. So in phase 1, we want to focus on that strategies, and jumping to the flashcards is not going to do it in phase 1. We have to let the development happen and not rush to that algorithm or to that rote memorization, and let the concrete ideas persist, and then get at different reasoning strategies for students. Like for instance, making 10 is a strategy. So students learn with experience. 7 and 3 is 10, 8 and 2 is 10, 6 and 4 is 10. So when they see 7 plus 6, they might think in their brains that 6 is 2 3s. And then we have a 7 and a 3, which is 10, because making 10 is a strategy, plus 3 more is 13. So they might get 7 plus 6 is 13 because they're thinking 7 plus 3 plus 3. 7 plus 3 is 10, plus 3 more is 13. We're doing reasoning strategies. And then we work on efficiency. So when memorization comes with meaning and understanding, then it's a powerful way of knowing. So another just quick example here is, imagine I asked you to memorize this number. I showed it to you and I said, memorize this number. It would be hard to memorize this number, wouldn't it? What if I broke it up like in phone numbers? We broke it up into this like phone number cadence. 159, 131, 72, 125 or something. I broke it up in some way to help you memorize it. Even then it would be hard to memorize. But what if I told you what this number really represented? This number is starting with 1 and then repeatedly adding 4. 1 plus 4 is 5, plus 4 is 9, plus 4 is 13, 17, 21, 25. What if you knew the pattern was start with 1 and then repeatedly add 4? 1, 5, 9, 13, 17, 21, 25, 29. You could go on and on and on. You could memorize a long number if you knew the pattern. This is just an example of how having an understanding helps you with the memory. And so, how do we support fluency development? How can parents help at home to support fluency development? Help children construct number sense by encouraging them to invent, share, refine informal strategies. I encourage you, watch that video of Adonis adding those 3-digit numbers. He has invented his own strategy. When you watch the video, you'll see he doesn't do it in the standard way, but for a first grader at his development level, it was a beautiful thing. Promote meaningful memorization of or master of basic facts. So meaningful memorization is not just rote, it's looking for patterns. 7 plus 6 is 13. Why? Because 6 is 3 and 3, and you can see those bonds. 7 and 3 is 10 plus 3 more is 13. Promote meaningful memorization. That's a good thing. Look at fact families, like doubles, like making tens. Leverage prior knowledge. When you get to multiplication, leverage addition. When you get to division, leverage subtraction, things like that. Even with addition, leverage place value understanding. Allow for some guided discovery and practice. Yeah, we want students to practice, but practice wisely. For example, if students have a mistake, like you saw my fraction examples, if students were practicing multiplication of fractions using the strategies that I shared with you, that would not be wise practice. They would be practicing an incorrect methodology, they'd be practicing incorrect thinking, and that practice would be detrimental. So make sure the practice is wise. Practice discovering patterns, practice looking at relationships, practice making sense of strategies, practice making these tens. So for instance, the idea, you'll see this in Adonis's video too, that he understands the making of 10. So we practice making tens so that later on we can practice adding 3-digit numbers, for example. So we have purpose behind our practice to lead to further discoveries. And don't rush to the formal algorithm. Be patient and don't push the student to that formal standard algorithm if they're not ready to go there yet. And parents can also support our students by listening to student thinking. Don't change it. Don't say, no, that's not how you do it. You're supposed to do it this way. Like with Adonis, I listen to his thinking and I will never tell him to not do it that way. I will not distract his way of thinking. I'll listen to it. I'll encourage it. I'll try to adjust it if need be, but I have to leverage where he's at, not just change where he's at. Avoid telling students how they're supposed to do it. Don't do that. Here I am telling you to not do something, and yeah, I know I see that contradiction there. But be careful that you don't tell. Like, what if I told Adonis, no, Adonis, don't do it that way, when what he did was fantastic. We just build on where he's at. Ask students to describe what they're learning instead of showing students what to do. Ask them what they're doing and have them explain it to you. Do math naturally. Anytime that you can be aware when you're in the car and you're driving, like how long will it be until we get there? Or let's count how many cars we see. Let's count how many of this we see. While you're cooking and you have measuring cups, there's fractions. While you're playing games, rolling dice, for example, in a game and adding up the numbers on the side. That helps students see numbers. It's called subitizing, when they just can look at the 6 dots and know it's 6 without actually counting them. So when you're playing games, you can do math naturally. And then so, of course, play games. Be positive about math. Always, always, always. Please be careful that you don't say, well, I was never good at math, or I don't like math. Be careful that you're always very positive, because we need math to live in this world. And have high expectations for your students. Now in this PowerPoint will be shared as well. There's some links to lots of resources, so please take a look at any and all of those resources as well. So building fluency is very important, and we want to have conversations around how we do it. Yes, it's an important thing. We do want our students to know basic facts, but we want to think about how that is developed over time, from kindergarten through 4th grade to 8th grade and even into high school. Thanks for listening.